there's four basic things that we need to consider when we look at NMR, okay? So I'm going to summarize them, and then I'm going to go back and hit each of those in a section. And I'm not going to try to drag this out too much, but I just want to make sure we're on the same page, because these are the four things that you need to know if you're not going to go on in chemistry. Okay? So in other words, if you go in to take the MCAT does have NMR on it. If you take the MCAT and you see NMR questions, they will basically be from these areas. Okay? That's it. So the advanced stuff that I teach you tomorrow would not be on the MCAT, in my opinion. All right? Okay, so let's look at these areas. So the first one is equivalence. Equivalent atoms, okay? The second one is integration. The third one is chemical shift. And the fourth one is splitting. Okay? And tomorrow, we're going to look at these areas again in a little more detail. So there's a basic level of understanding, which will get you through probably 90% of everything you ever needed to know about NMR. And then there's advanced stuff that if you were a chemist or doing organic chemistry or whatever, you would need to know this additional stuff. Okay, so we'll cover the advanced stuff tomorrow. For today, we're just going to hit this on a very straightforward level. Okay, so first of all, atom equivalence. Now, we're going to focus on hydrogen equivalence, but effectively, atom equivalence is a general property of atoms that are covalently bonded in a molecule. So when we do carbon NMR, we talk about equivalent carbons. We're going to do hydrogen NMR, what we call proton NMR, talk about equivalent hydrogens. Okay? All right, so first of all, a definition, okay? It's a wordy definition. Okay? So blah, 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 blah. And you guys don't have to jot this down if you don't want to. You can. I am going to post these notes. But basically, here's the concept. We have a molecule that's got carbon and hydrogen bonds in it. So we say, here's a hydrogen. What if I replaced that hydrogen with some group X? Okay? Now I look at another hydrogen. What if I, instead of replacing the first hydrogen, I replace the second hydrogen with X? So when I replace the first hydrogen with X, I get a new structure. When I replace the second hydrogen with X, I get a new structure, right? So I've replaced each of them one at a time and then put it back to a hydrogen after I did, right? Then I compare the two structures, or maybe there's more structures, and I say, are they identical, right? And comparing structures, it was a skill that we talked about very early last semester. We started with constitutional isomerism, right? To have the same connectivity, but then we looked at stereoisomers, and it turns out that if they're stereoisomers, if they're constitutional isomers, there's a good chance they're not equivalent. There's one exception to that. We're going to talk about all of that stuff in more detail because there's some terminology and definitions tomorrow, okay? There is another way that hydrogens can be non-equivalent. It's also a three-dimensional effect. We're going to talk about it tomorrow. They can be not magnetically equivalent. This is generally called chemical equivalence. Okay? So tomorrow we're going to talk about magnetic equivalence, and we're going to talk about also stereoisomer non-equivalence, like if the two things are diastereomers. Okay? All right, so let me show you an example of this. Okay, or some examples, just really quickly. Let me make it a little more sophisticated. Okay, so this is the kind of really simple question in this area, but then, well, just like, you know, when we did, are these two things identical, but then we use that as part of other problem solving, we're going to have more complex ones, okay? So, are these chemically equivalent? So, what we're going to do is we're going to do what's called the substitution test. Okay? We're going to replace each with some imaginary group or atom X. Okay, so here we go. Sorry, I'm going to add and compare, right? And I put an H there, and I didn't mean to put an H there. I meant to put an X there. There we go. Right, so I replaced hydrogen 1 with X. Now I replace hydrogen 2 with X. Okay, and then what I do is I ask, what is the relationship? And again, that's a skill that we worked on in first semester lecture class. And by now, I'm sure you can look at them and just say that these are clearly identical structures. Right? And so what we would say is They're identical. So hydrogen 1 is equivalent to hydrogen 2. Okay? Pretty cool with that? Now, I'll be honest with you. This is sort of the long way, right? You could have probably done that in your head. If you can do it in your head, do it in your head. Okay? But if you're having problems, this is the long way to work it out, right? Okay? All righty. So then, excuse me. So in most cases, the 3 hydrogens of a single methyl group are equivalent. And I'm sorry that I ran out of room. I'm going to do my examples. So I'm going to do a really simple example, guys. Okay, so notice that this is basically a methyl, right? It's a CH3. So if we do our substitution, and I'm trying to write this sort of efficiently here, so I'll come back and put the X's in. Since we're comparing all 3 hydrogens, we have to do 3 substitutions, right? And then we ask the same question, relationship. These are all identical structures, right? Okay. So what that means is we don't usually have to do these methyl group equivalent substitutions, right? We can just look at a methyl group and say, at least those are all equivalent, always, right? Pretty much. Okay.
Can you give us please any
Some examples of them non-equivalent for methyl group or for other ones, Sam?
for methyl group?
Oh, that's a good question. Honestly,
or is it like rare to be?
it's so rare that I'm coming up blank with one.
That's fine.
I'm coming up blank.
It's fine.
Yeah, there's probably, I'll show you some interesting cases tomorrow where 2 methyl groups that are attached to the same carbon, usually 2 methyl groups attached to the same carbon are equivalent. But in some cases, because of stereoisomerism or magnetic magnetic fields being different, they become non-equivalent. I'll show you some of those tomorrow. We're going to talk about stereochemical isomerism or non-equivalence tomorrow. Okay. All righty. So that's our basic equivalence. And so the last thing I want to talk to you about is I have 2 things. I want to give you a piece of terminology and then a way to draw pictures, okay? Piece of terminology. Excuse me. I don't know, I put the word so there. That's sort of weird, but okay. A group of equivalent atoms, what we're going to call them is a unique set of equivalent atoms. The idea being that they're unique, which makes them different from other sets of equivalent atoms, right? So like if I had a CH3, those are one set of equivalent atoms. Then if I have a CH2 that the two are equivalent, that would be a different set. And so that's why each one is a unique set, right? So that we can say there's, you know, how many are there, right? I know it's a big term, but it's an attempt to be very concise. Let's see. So what organic chemists do when they do unique sets of equivalent atoms, I'm going to show you some of these here, okay? I'll show you an example with a little bit more complex molecule, okay? No. I think I'm gonna leave it like this, okay? So we look at this molecule, okay? Can you guys see this? So what we want to do is we want to say, okay, like we want to find each unique set of equivalent atoms, right? And then we want to mark them so that we can count up how many total different unique sets there are, okay? So what we do is organic chemists do this, and if you look at some like scientific papers and textbooks, you'll see this done, okay? They assign a lowercase letter. So for example, we said that in most cases, pretty much all the cases we can think of, hydrogens that are all on a single methyl group are going to be equivalent to each other. So we'll call these three hydrogens unique set A, okay? Those are going to be different from the CH2 hydrogens, right? So that's a second unique set, so we'll call that B, okay? All right, sorry, blobbed that up. Okay, now I want you to watch this. This is kind of interesting. So now we have our aromatic ring, right? We're attached right there. Sorry, it's sort of, okay. Do you see, it turns out you can prove this. If you were to substitute this hydrogen or you were to substitute that hydrogen, those would create identical structures because you could just take the molecule and go like that. So this and that are actually equivalent to each other. Similarly, this and that are equivalent to each other, and then this is different. So that molecule has 5 unique sets of equivalent hydrogens, right? So now imagine there's 2 test questions or questions, right, that I can ask you about this. And this is what I was talking about, how like on the MCAT or something. Okay. So the first question would be, how many unique sets of equivalent hydrogens, right? Just how many? It's a number, 1, 2, 3, 4. In this case, it's 5, right? The second question would be, here's a structure, right? Indicate each unique set of equivalent hydrogens by assigning them a letter, right? So in other words, I give you a picture and you have to write the letters on. Does that make sense?
Yes, it does.
Okay, perfect. So again, that's basically the level, that I would expect to see on an MCAT question for this, but we're going to use this later on. Okay.
Professor, if we were to add a methyl group to anywhere in the ring, it's going to change the whole unique sets, right?
Exactly.
Can we add a methyl group and then see how it's going to be how?
Absolutely. Let me do that real quickly. Okay. I'm going to put it right here. Okay. So I'm going to do this really quickly. There'd be A, there'd be B, and this, it doesn't really matter the order, right? That would be C, right? Because the two methyls themselves are not identical, right? Okay. Then we have these other hydrogens. Well, this one is clearly different from all the rest, right? And now we have this one, it's next to the ethyl and far away from the methyl. This one is next to the methyl and far away from the ethyl. So we get that, right? Now, I do want to also make a comment about these. NMR instruments have there's different strength ones, and we're going to talk about that again tomorrow, okay? The strength of an NMR instrument. The ones that are weak, the peaks are really fat. And so when you have two that are close together, they sort of broaden into a blob. Does that make sense? So that you can have a situation where like two signals look just like one really fat one, okay? So what we see is these hydrogens on the benzene ring that I've labeled C, D, E, or E, F, G, A, okay? Often in a weak NMR, we're not going to see a separate signal for each. They're going to kind of be blobbed together. But in a powerful NMR, and this is one of the advantages of a powerful NMR, in a powerful NMR, the signals become thinner and thinner and thinner. So what happens is the blob separates, and we can literally see each one. Okay? So, all right. Now, next, integration. Did I put a number or what I? Okay. Okay, so here's the idea of integration. Oh, sorry. I didn't lose you guys, did I? Okay, good. So why do we care about sets of equivalent hydrogens? Because each set of equivalent hydrogens should give a separate signal in the NMR. Okay? So when we look at our NMR spectrum, if I have 5 sets of unique hydrogens, I should have 5 signals in my NMR. Now I call them signals because when we get to splitting, we'll see that a signal can be split up into multiple peaks, but they come together. Okay? So it's this group of peaks. Now, what integration then says is weird stuff going on. Okay, so this is something that comes from the fact that NMR instruments were first invented by physicists. Okay, or let's say, you know, really or they were invented by chemists / physicists that understood a lot of physics, and a lot of physics is very mathematical based. Okay, so I don't know how many of you have had calculus, and if you haven't, you don't need to worry about it. But in calculus, we do something called integration. And integration is basically you plot a curve and then you measure the area under that curve. Okay? So here's an example of 2 curves, right? So what we're basically saying is it's the area in that section of the curve, right? And if you haven't taken calculus, if you do ever take it, you'll see that, yeah, that's the physical interpretation of that mathematics. That's what that thing is giving us, the information it's giving us. Okay? So in the NMR then, the key here is that can you guys see that? So I was going to give you an example of integration, and I don't know where I got lost. So I've already written it out. This is a really simple molecule. It's ethanol, right? There's 3 sets of equivalent hydrogens. Let me just sketch what the NMR would look like for this. Not going to be perfect, but it'll be close. Oops, didn't make it long enough. Okay. So we're going to have something that's going to look like this. Sorry, these need to be bigger. Oops, sorry. That's not right. Oh, I made those way too big. All right. I'm sort of trying to exaggerate here or like really show it. And then somewhere in this region, I'm just going to do it right here, is going to be a blob. All right. Now what this represents then is I'm going to put my labels next to them. This is why we label them. So now we can say, here's hydrogens B. This is the signal for hydrogens B. This is the signal for hydrogen C. This is the signal for hydrogens A. Okay. They're probably not to scale. This would be what they would look like in a really weak NMR. As I said, in a really weak NMR, the peaks are kind of broader. In a more powerful NMR, they'd be like a lot closer together and a lot narrower, okay? At any rate, what we would see is that hydrogen C is only one hydrogen, right? So the computer would calculate a number for that area, okay? And that number might be something like, let's say, let me pick something that's not ridiculous, but that is not quite so straightforward. Let's do 45. Right? In other words, there's going to be units or something. It's going to calculate a number, okay? So this one, if that has an area of 45, this would be an area of 90, and this would be an area of 135. Okay? Now you're looking and saying, what does that mean? I don't, where those numbers are off the wall. Those are just like you measure the area, that's the area, right? But what's important is the ratio of those areas. Okay? That makes sense? So in other words, what we do is we find the smallest one, which is 45, and we divide them. Oh, sorry, I should say 45. So do you see that's a ratio then, right? So this one, for example, is 2. This one is 1. This one is 3. Do you see? So those ratios give the ratios of the number of equivalent hydrogens, right? Now, sometimes when you do this, you get a ratio like 1.5. To get those to work out, you have to have them all be whole numbers because you can't have half a hydrogen. So you'd multiply all those ratios by 2. Those would be the actual number or say of equivalent hydrogens. Does that make sense? Now, when we do this then in the actual NMR, there's 3 different ways we can be presented with integration data, okay? From hardest to easiest, okay? So the first one is the hardest, where you're just given the numerical values for the area that was calculated by the computer, okay? Then you have to do the division, and then you have to get them into whole numbers, and then you also have to figure out if there are symmetries that cause those to be multiples of those whole numbers, okay? Make sense? Then the next easiest would be to be given the ratios, but not guaranteed that it's the actual number, because the actual number could be a multiple of those ratios. Kind of like molecular formula and empirical formula, right? Empirical formula is the lowest ratio. Molecular formula is then maybe it's a multiple of those, okay? And then finally, you could be given the actual number of hydrogens, and usually in the NMR, if we're indicating not the ratio, but the actual number of hydrogens, we put the letter H after it. Okay. So if you're just given like 2, 3, and 1, you're not guaranteed that there are exactly 2, 3, and 1 hydrogens. You have to look at other information. But if you're given 2H, 1H, 3H, you're guaranteed that that's how many hydrogens there are in that, giving that signal, in that set of equivalent hydrogens giving the signal. Okay. So that's integration. Any questions about that? Everybody good?
I was just wondering, Professor, why when you draw the B
Yeah.
set, why did you put 4 peaks?
Because of splitting. So we'll get to peak splitting in just like 5 or so minutes. But what happens is when equivalent hydrogens like hydrogens A, see, sometimes we do that. We circle them all out and say those are all the same. They are adjacent to a carbon with other set of hydrogens. So this is hydrogens B, right? A and B, their signals interact and they split, they become split. So instead of being one peak, they split into multiple peaks. But they're all peaks, all part of the same signal, just a signal that's chopped up into smaller chunks, okay? That's why I use the term signal, right? So this whole thing, this is a signal for hydrogen B, and then these are actual peaks. You see the difference? So the only signal that's going to give just one peak is this one, which doesn't split. And we'll talk about why that's the case. It's a special example. I'm going to give you just a rule today, but then I'll explain it tomorrow. Okay?
Dr. M, quick question.
Yeah.
Say you're to add another CH2 in between, right, for this example.
So let's say
it was CH3, CH2, CH2OH.
Okay, so like one propyl instead of
yeah.
L. Okay.
Are those the CH2 hydrogens are no longer identical, right?
That's correct. So we would have A, B, C, and D.
And then those will also have different signals on the NMRs that will show up.
That's correct. They'll come at different locations because their electron densities will be different.
Right.
And they'll be split differently. So this one in particular is going to be split up into a lot more peaks. It's going to actually be split up like this. We split into 6 peaks, okay? Because of the number of adjacent hydrogens, and we'll talk about that.
Right. Thank you very much.
It would be much more complex.
Okay, thank you.
Okay, everybody cool with that? Okay, so now, next topic. This is 4. By the way, guys, let me ask you guys something. Do you guys follow the, do Roman numerals make sense to you guys? Were you guys taught Roman numerals?
Yes.
Yes.
Okay,
Yes.
okay, good. I just, because, dude, my nieces, okay, can't read cursive writing. Like if, maybe you can't either, I don't know, but you know, there you can write in like block letters like I write, or you can write in cursive where it all kind of flows together. I'm terrible at writing in cursive because I don't hold my pencil right, and so it's all jerky. But my nieces can't even read it. I guess it's not being taught anymore, and so I just sort of worry about it, which is fine. It's not. I mean, dude, I don't think it's like a life or death skill or anything if nobody's using it. But on the other hand, I don't want to be using things that you guys don't understand, right? Like, oh, what's that crap he's writing there, you know? So, all right, good. Okay, next, chemical shift. we're going to talk more about the theory of NMR tomorrow. Okay. So I'm just going to give a real brief explanation of this, but okay, so I know that's a big blah, blah, blah. Okay, so we're going to talk tomorrow about how the NMR signals are actually measured, because there's a little bit of stuff then, if we kind of understand how they're measured, we can start to understand why they behave the way they do, okay? But we don't need to know that right now. Right now, all we need to know is that the frequency, in other words, where it shows up on the NMR scale, all right, is going to relate to the electron density. So in other words, if I have a hydrogen atom, it's got an electron cloud around it, and I'm going to draw that in just a little bit, okay? That electron cloud affects what frequency it is. And the relationship is actually pretty straightforward for signals that come below about 5, okay? So here's the relationship. Okay, so let me draw a graph here, and let me just okay, now so what this means is that what we're going to do is we're going to start here. This is our basically it's our reference, I guess we'll call it our reference frequency. I got to go look at what the exact term for this is, because there's two different basic frequencies, okay? And then what we see is in this direction, the frequency increases. So up here we have a high frequency, and down here we have low frequency. Okay. And actually what we measure is the difference between the frequency for the signal and the reference frequency we take. Okay. So we basically measure how far is the signal shifted over from 0. Okay. And then we take a ratio, and then that's how we get our parts per million. Okay. Okay. Everybody cool with that? And you don't have to do that math. I'm just trying to give you an idea of what the numbers mean. All right. So high frequency on the left, low frequency on the right. So it turns out that if we look, high electron density causes lower, what that means is on the right, this is high electron density. And then this is low electron density, up to about 5. Well, after 5, we're going to see there's another thing going on with magnetic fields. Okay, so this is not perfect. All right, everybody cool with that? Okay, so what do I mean by that? Well, electron density changes when we put in different electronegativity atoms. So let me show you an example here. So let's say we have a hydrogen atom. What I'm going to do is I'm going to represent the cloud of electrons with a circle like that, and I'm going to color it in. So this is kind of what I've talked to you about, how really in organic chemistry, I think it's often more useful to think of electrons as a cloud rather than a particle, right? And you can see that this cloud, the shading is really dark. That means there's a lot of electron density, right? Okay, so then if we compare that, if I put a chlorine right here, okay, then what's going to happen is the chlorine pulls electrons because it's electronegative, right? So it takes electrons away from the carbon. Then the carbon takes electrons away from the hydrogen, right? And so what we get is, oh shoot, I meant to do that in blue, sorry. The cloud is less intense, right? We get a Does that make sense? And so that's how we can visualize it. Just like how intense is that cloud, right? It's like a gas or something like that, or like the fog, right? If the fog is really thick, you can't see through it. That's dense fog, right? If the fog is really thin, so it's sort of transparent, translucent, you can see through it. That's not very dense, right? Same kind of thing with electrons. Now, this kind of electron thing, this is called an inductive effect. Okay, it's just a term we're going to use again in second semester called inductive. Okay, an inductive effect is electron withdrawing or donating. Technically, it happens through the sigma bonds. You see how the arrow is really showing how the sigma bond is actually pulling the electrons, right? The single bond. Okay, and it's caused in this case by electronegativity. But if I were to put an atom in and put a positive charge on that atom somehow, it would also pull electrons away. Okay? All right. But here's the thing. Let me see. Actually, I'm going to say this in the reverse order. So there's two things about inductive effects that you need to understand in order to see how the chemical shift works in the NMR, okay? Once you get these two concepts, the NMR table and everything will make more sense, okay? So the first one is that, and I'm going to draw a picture here. Okay? And what I'm going to do is I'm going to imagine we put a fluorine, an extremely electronegative atom right there, okay? So then we look at our electron densities. Okay? So fluorine is pulling here, and then it pulls here. Okay? Do you see that this one here, this is a two-bond effect, right? It goes through one bond and then a second bond. You follow me? This is going to be the strongest. This atom will have a very low electron density. Okay? If we go one more bond away, oops, sorry. This is a three-bond effect. So what's going to happen is it's not going to be as strong. So this atom will have a little bit higher electron density, right? This is the four-bond effect. And then this would be 5 bonds. And then this would be just a hydrogen by itself, okay? So this one is going to be the most dense. It's going to essentially be the same as the hydrogen by itself, okay? Sorry. Okay? Right? And then this 4-1 is going to be in between, and I drew the 5th one so that I could get the 4-1 darker, but not as dark. Okay? Does that make sense? So what we would then expect is that if we looked on our NMR graph, so the 2-bond one would be right there. Okay? The 3-bond one would be here, just a little bit below 2. The 4-bond one would be here, just 1.3, 1.4, and then the 5-bond one and the one by itself would be here, let's say at 0.9. Okay? So this would be like 3.8. This would be like 1.9, 1.3, 0.9. Do you see as the density increases, it moves farther and farther to the right. And when we look at the correlation table, that's where those numbers come from, basically. Everybody cool with that? So there's tables of these things, right? And I'm going to have to put the correlation table. But let me do one more thing. Because this is one of the things that confuses people about the table. All right? I'm just going to do this because I know these numbers pretty well, okay? So this is our 2-bond inductive effect with 1 atom. And I put that second arrow in the wrong direction. Sorry, should go this way. Do you see that? 2 bonds, right? But what happens if I put a second chlorine? Well, the first one is pulling, the second one is pulling. So now what I get is a pull and a second pull. Do you see that? So the electron density goes down even more, okay? What does that mean? Well, that means that this one, if this one is at 3.8, this one is going to be up around 5.2. Okay? This is the problem with NMR correlation tables that we don't have quite so much in the IR one. when you look at the NMR correlation table, it's going to be telling you like the general, like if you have a thing pulling, it's approximately here. But a lot of tables, and in fact, my basic table doesn't have this. It doesn't account for what happens if I have 2 chlorines pulling, right? It doesn't account for the fact that these add up. And so you're not going to have an entry exactly where that peak is, or that peak is going to come here, but it's not really for this thing. It's for a tube of other thing. Okay. So that's the thing. So, but, and I don't have one right now. I'm going to get one. We're going to do a simple one. And then after tomorrow, we're going to do a more complicated one. Okay. But that's the problem with the correlation table. Okay. Last thing, you guys are super patient. I totally appreciate it. I'm sure you guys are getting totally bored by now, but I've got good news for you. So after this, so, okay. Last thing, peak splitting. Today, we are going to do the simple explanation of peak splitting, okay? Now, I have a really straightforward way for you to visualize and use language of peak splitting, okay? So trust me. I call it my analogy of people in houses, okay? And it's going to look really ridiculous. And then when you see how it works and it gives you the language, you're going to say, I totally get that. I can totally do that. All right. Okay. So let me show you my analogy. It's based on a picture. So let me draw the picture first, and then we'll do the analysis of the picture. Okay. I like to do 3 houses. I can do as many houses as I want, but 3 usually gets my point across. So those are houses, right? So now what we're going to do is we're going to put people in houses. Okay. All righty. Then we're going to ask like these really simple questions. Okay. So the first question we'll look at each house, how many people are in the house? So if we look at the first house, see 2 people, right? Second house, 2 people. Third house, 1 person. Do you see that? That's not a hard question, is it? Okay, second question is, how many next door neighbors? Now, I need to qualify this. Technically, in the English language, right, if you say neighbors, right, like the people that live across the street are neighbors, right? The people living 3 houses down are neighbors, right? Neighbors, just in a general word, means people living near you, right? But then we can talk about how many people are living in the house directly next to mine. We call them next door neighbors. Okay? In peak splitting, they use the term neighbors. But when they use that term, what they really mean are next door neighbors. Okay? Does that make sense? Okay, so what we have to do then is we look at the house, but do you see that we're not asking how many people are here in the house? We're asking how many people are here. So in this case, the people here have 2 next door neighbors, right? In the second case, the people here have 2 on one side plus 1 on the other. So they actually have 3 next door neighbors. In the third case, there's only 1 person here, but they have 2 next door neighbors. Okay? So the next door neighbors is something, it doesn't depend on how many people are in the house you're looking at, right? But it really depends on the houses nearby and also sort of their order, like how they're arranged, right? Like this house here in the middle, because it's got houses on either side, it has a different number of neighbors than this house on the end, right? Even though inside these 2 houses, there's the same number of people, right? Okay, so what we're going to do then is we're going to look at the exact same thing, but now instead of drawing houses and stick figures, we're going to use carbons for the houses and hydrogens for the people. Okay? And I'm going to use an approximation here that I'm going to say in this example, okay, all the hydrogens that are living in the same carbon, okay, that are attached to the same carbon are going to be equivalent. And there's not like a second carbon that has also other ones that are also equivalent, okay? That's the complication, all right? So we look here, we say, how many equivalent hydrogens are there? Well, there's 2, right? And effectively, there's 2 hydrogens living on that carbon. 2 hydrogens living in that house, right? Here's another house. How many hydrogens? 2. Here's another house. How many hydrogens? 1. Okay? Then we're going to ask, sorry, that's supposed to be a letter N. We're going to ask how many neighboring hydrogens, call that letter N. So do you see here? Here's the house. Here's these 2 hydrogens, but we're going to look next door, 2 neighbors. Here's the house. Here's the 2 hydrogens. We're going to look next door. We got 2 on one side plus 1 on the 3 neighbors. Here's the house. Here's the hydrogen, but next door, 2 neighbors. Okay? Everybody cool with that? So, and in the NMR splitting thing, we talk about neighboring hydrogens. That's the correct term. Neighboring hydrogens. We symbolize it with the letter N. Now, what is the number of equivalent hydrogens on the house? Well, that is basically our integration. Right? We said integration tells us how many equivalent hydrogens there are in a group of equivalent hydrogens, right? So effectively, in not all, but in the majority of cases, that's just how many hydrogens are attached to this carbon that are different from the number of hydrogens attached to that carbon, right? How many people living on that carbon, hydrogens living on that carbon. Okay, so now, how does splitting work then? Sorry. Okay, now we're going to see this is not perfect. There's exceptions to this, but we're going to talk about the N+1 rule. And the N+1 rule says, sorry, shouldn't say peak, should say signal, and I will fix that. All right, so let's look at an example. I'm going to go back to an example I used earlier, okay? Because it came up, right? And then it'll also give me an opportunity to tell you one of the first of many exceptions to this rule that we'll cover in advanced NMR tomorrow. Okay? But this is the simple rule. It applies in a lot of cases, and it's definitely probably as sophisticated as the MCAT would ever expect you to know it. Okay? So let's just take a quick look. We have hydrogens A, B, and C, right? So my integration is going to be 3. It's going to be 2. It's going to be 1, right? So set A has 3 hydrogens, set B has 2, set C has 1, right? My number of neighbors is going to be like this. Here's these 3 hydrogens. Here's the house next door, okay? 2 hydrogens, 2 neighbors. Here's these 2 hydrogens. Now, here's the thing. Hydrogens that are on oxygen or nitrogen won't be neighbors because of an effect that I'm going to talk about tomorrow, okay? For right now, just understand they're not neighbors. So what we have here then is if we look at these, there is a hydrogen on that side, but it's not a neighbor. So we only have these 3. There's only 3 neighbors, right? And then So these OH hydrogens and NH hydrogens, they behave differently. They don't act like neighbors and they don't have neighbors. Okay? All right. So now, so what will the peaks look like? Well, what the peaks will look like then is this. So I'm going to go back. Okay. So if we look, do you see here we have this and then that, right? There's a 2-bond electronegative atom. Do you see that? So that means that the electron density of these is going to be very low. They're going to be between 3 and 4. That's what the table will tell us when we look at the table. Okay? And they have 3 neighbors. So three neighbors is 4 peaks. So they're going to look like this. And the peaks actually have a specific shape, and they would probably come about 3.8, and it would be 4 peaks. This is hydrogens B, okay? Now, if we look at these hydrogens, do you see that these are 3-bond? So remember how we talked about 3-bond is not as big an effect? They're going to be about 1.9 or so. And they only have 2 neighbors, so they're going to have 3 peaks. So it's going to look more like this. Right? Say 1.9, 3 peaks. Now, the oxygen OH changes its position depending on the concentration for reasons we'll talk about tomorrow. So I'm just going to pick a place. It's just going to be a blob right there. That's going to be C. Do you see? It's going to have 1 peak. Because when you have 0 neighbors, 0 plus 1 is just 1. Okay? Alrighty. I think that's enough for you guys to get this. Now, what's going to happen is, and this is the big news here. So I'm going to stop sharing. I will post these notes. I will post this lecture. Okay?